Okay, hello everyone again. So, is it playing? Okay, yeah, okay. So, so I will be presenting my project entitled Enhancing Urban Mapping with a Multi-Sensing Micromobility Platform under the supervision of Dr. Amir Hadachi. So, for this, I want to begin my presentation from the very end and walk you through the process on how and why I reached this point that I am right now. So what you see here is my best attempt in developing the cutting-edge multi-sensoring capturing mobile platform, which I called Delta. And Delta stands for Digital Enhancement for Localization in Tartu area. Now, the main objective is to create a rich multimodal data set of Tartu of commonly overlooked urban spaces such as sidewalks, cycling lane, and pedestrian routes. Now, this data set has a wide range of applications such as urban planning, mobile robotics such as food delivery, parcel delivery, last mile delivery, and micromobility services. Next is the quality of the data. Now, the quality of the data was the top priority from the get-go. Thus, all the sensors are configured and mounted on multiple damping and vibration isolators in order to effectively mitigate any vibration, any noise interference as much as possible. So one of the uniqueness of our platform is the integration of an omnidirectional microphone. Now this enables us to capture the often overlooked acoustic modality of the city. Now tapping into the acoustic modality combined with the visual data adds an extra layer of context to our 3D map. Now, this provides us a valuable insight in the acoustic patterns of the surrounding. Now, using the acoustic patterns of the surrounding, it allows us to understand the city's rhythm, the crowd density, the type of activity, and the nuances in each region. Now, to make it more clear, I here provide a few examples. So, for example, urban planners can use this data to understand how people use public spaces, or they can use this data to understand where the most significant foot traffic occurs, or understand how different regions of the city are utilized throughout the day. Now, another example would be micromobility and autonomous vehicles, which they can use this acoustic pattern to understand their surrounding and identify areas with higher pedestrian density, or detect any unusual sounds, which can indicate a potential hazard and allow them to navigate intelligently in these complex environments. Nextly will be the modularity of the platform. So the platform has been designed to be modular, and this will effectively allow us to rapidly expand and configure so that it may be improved at any time. So it will make it perfect for dynamic research environments where new requirements and technological advancements are very typical. Now, after this, I want to share the motivation behind my effort, starting with my work. So localization is the central theme of my doctoral research, is about determining the spatial coordinate and orientation of an agent with respect to a point or an axis. So to an axis. Then the domain of localization can be categorized into two main subjects, vision-based and non-vision-based localization. Now, in the realm of vision-based localization, we have stereo camera and monocular cameras as the dominant capturing devices in this area. And for non-vision-based localization, we have technologies such as GPS, GNSS, inertial, and odometry and LiDARs that are used in this field. Now, my focus in this research will be on monocular-based localization or just image-based localization. Next, we will explore the monocular-based localization. In the next, yes. So monocular-based localization can be classified into two groups, unknown environments and known environments. For the unknown environments, techniques such as structure for motion or SLAM are typically used. And for known environments, which is the focus of my research, it is further broken down into two main categories, one 2D to 2D and 2D to 3D based localization. Now, the term 2D here carries a dual significance. Firstly, it signifies the type of data inquiry, which is in this case is a 2D image coming from our camera sensor, and secondly is denotes the 2D georeferenced image from an existing data set. And finally, the 3D term here refers to the 3D model or 3D representation of the environment. So next, in order to proceed with localization, we realized that we have to have a data set. Now, this gives us two options. Either use an existing data set, such as Kitty or New Scenes or Cityscapes, or create my own. And as you may already know, I chose the latter to create my own data set from scratch. So in order to be more aligned with the objective of my study, which is mapping sidewalks and pedestrian routes and cycling lanes. Now, to proceed with the 2D georeferenced data set, what we have to do is take images from different locations of the city and associate their corresponding geo-coordinate points to each image. Now, by doing so for the entire city, what we establish is that we establish a 2D georeferenced data set for the entire city. So next, we will turn attention to creating the 3D data set. So before we delve into the creation of the 3D data set, we have to ask and address three main questions. One is, which type of 3D representation are we going with? What approach are we going to use? And at what scale are we going to work with? Now, in my case, I will be focusing on learning-based 3D reconstruction for large-scale environments. Now, the manner we choose our 3D representation is crucial because it influences the type of neural network that we will use. Hence, in general, we can categorize image-based deep learning for large-scale 3D reconstruction into three main categories. One is volumetric, geometric, and implicit representation. Now, one example of volumetric representation is voxel representation. Now, voxel representations discretizes the 3D space into voxels or 3D cubes. They are analogous to 2D pixels in images. However, they cannot faithfully represent the fine details. Now, nextly is geometric representation, starting with point clouds. Now, point clouds are a collection of data points in a 3D coordinate space, which every point represents a specific location in space. Now, point clouds can provide a high accurate representation of the environment and the 3D object. Now, next method in geometric representation is through mesh representation. Now, mesh representation is a collection and set of points and vertices and edges which basically collectively define the surface of a 3D shape. Now, meshes are considered more efficient compared to point cloud in terms of processing and storage. Now, beyond explicit geometric and volumetric representation, we have deep learning models that can encode an entire 3D scene into implicit representation. Now, in the context of implicit 3D reconstruction, we have there is a technique called neural rendering models, which learn to understand the structure of a 3D shape in an indirect manner, without explicitly defining the edges, vertices, and surfaces. Now, one such method in this category is neural radiance field, or NERF. And now this NERF are very powerful, and they are able to represent a 3D scene in a very detailed, high-level way. Now, for my dataset, the main focus will be on a point cloud and mesh representation, even though the potential of nerves will be explored down the road. Now, the entire dataset will contain a wide range of data sources, including stereo image sequences for tasks such as visual odometry, depth estimation, point cloud, and mesh generation, and also a 360-degree audio recording. It also features point clouds from LiDAR and 4K wide-angle footage from across the city. And lastly, it will contain GPS data points as well. Next will be the development of the platform. Now, the development of the e-scooter platform was an interdisciplinary work. It required a lot of 3D designing, 3D printing, electronics, power management, software development, lots and lots of iterations, and most importantly, making everything work together. But during this process, a particularly noteworthy achievement emerged, and that was the development of an optical flow-based positional tracking sensor. Now, the aim of this sensor is to accurately, precisely track the changes within the X and Y axes and translate these changes into latitude and longitude in real-world coordinate system as the e-scooter moves. So, it achieved this by initializing the starting point of the e-scooter, and as the e-scooter moves, the sensor tracks any changes within the direction and position of the vehicle, and what happens is that it will effectively update the initial GPS point with pixel level accuracy. Another interesting aspect that I felt it's worth sharing is the documentation process. Now, when developing the documentation, I had a specific criteria in mind. I wanted a system that would allow me to track my progress, allow me to detail my methodologies, and also allow me to embed any multimedia content that I want within one platform. So eventually, I settled on Miro. This is the online collaborative framework which allows you to embed links, text, images, videos in a graph-style manner. Now, this will allow you to see the connections, the relationship between components and different aspects of the system, and broadly allow you to see the big picture at a glance. Now, what you see here is a continuous evolving process in which regular updates are applied whenever a sensor is added or any changes has been done to the system. Now, documenting my work this way, I realized that how this graphical form of documentation helps me to navigate and manage a complex system such as this very efficiently. Now, here, I could demonstrate a short example in the documentation in action. So, for example, we want to explore the 4K synchronized camera. We can see that it's connected to the main board, and then we are presented with different components related to the sensor, such as the 3D design, how to get started, how to access with OpenCV, and the full data sheet. So, after reading the full data sheet and understanding what's going on, then we decide to, for example, explore the 3D design aspect of this. Then we navigate to it, then we are presented with the progress of the design and the final version, how it evolved to be that, and what software was used in the process, and where I can find the files, all in one framework. And another one is the implementation of two additional sub-documentation within the main documentation. That one outlines the power management and the other detailing the optical flow-based positional tracking system. And having this kind of powerful all-in-one framework really enhances the seamless communication of your ideas to others, and really enhances the clarity and efficiency of the process. Now, finally, the ultimate goal of my project is is to combine everything that I have learned, all the skills and knowledge that I have gained onto one platform, a platform that serves a dual purpose. So not only it provides a secure way of transportation, it also allows for the development and for the frequent development of and updating of the urban mapping as it navigates across the city. Thank you, that's it.
Wow, there went half a year of work for making the presentation, I guess.
Yes.
Yes, you admitted that. Oh.
Yes. Okay, should I go?
So he should definitely get the best visualizations award. I don't know how you create those, but okay. Any questions? There. Oh.
Yes, thanks indeed for the very inspiring video show. So I just need to understand a little bit more about the research aspects. So it looks to me like a very good engineering project that you're doing. So building a device that I assume nothing comparable is existing at the moment, I suppose?
Yes.
So what are the parts that are really particularly, let's say, innovative? And who would be, I mean, I guess once you're finished with your PhD, somebody else will use it also maybe outside research. I mean, I imagine it can be used also for very practical tasks, but what would be those tasks, and how is it, particularly how is it cost effective? I mean, I imagine there are many other ways on how you could do mapping, right? And I guess you might have compared it to other approaches and figured out what are the pros and cons and so on. So maybe you can share a little bit about this. So what is now the particular advantage of this tool, and how will it be used, and who will use it, etc.?
So the main contribution of this is basically a few things. One of them is the integration of or augmenting the audio within the 3D map. So when we create a 3D model or 3D representation of an environment using conventional methods, what happens is that you have to remove dynamic objects. That means humans, cars, and other things that move should be removed after you map, because then you could have a proper 3D model. Then when you remove those things, what happens is that you're actually removing context from the 3D map. Now this is reserved for the audio. That's the idea. So when you remove those and then create your model, the data will be reserved in the audio. So then you could use audio segmentation, such as classifying what you hear, like running, jogging, what type of vehicle is going past, like scooter, bicycle, whatever. Then you can augment those in specific regions. Now those could be used for different applications, as I mentioned here, like micromobility services, parcel delivery and food delivery robots, which are no worries, Yes.
It's exactly very nice that you mentioned it, because it was quite at the beginning of the talk when you talked about this audio.
Yes.
I didn't really quite get why it is not easier to just have a vision. I mean, like, look at images and then you see what objects are moving around. Why do you need audio?
Okay. Yes. So first of all, if you want that kind of image, it is first of all there are a few aspects to it. If you want to do image recognition, you have to do you should apply behavior recognition, and that you need a temporal kind of a frame, and you need a whole 360-degree kind of viewing angle to do that. And the computation that you have to do for identify someone is running or what is going bypass you, it's much more expensive than audio. So, for example, an audio is a 1D signal, what an image is, okay. Okay, thank you so much.
Hi, I have a question regarding the trade-off between using this audio, because I guess that for audio you also need high competition to understand and to basically guess what is the audio representing, if, for example, a person running or so on. So what is this trade-off in terms, for example, the accuracy, for example, in distinguish between a car passing by or a motorbike, for example?
Do you mean the difference between the computation of audio and image?
Yeah, and also what is the this trade-off between the accuracy of the, because an image is pretty accurate, like image
Yes, what
recognition.
one image is not accurate. You can't do with one image. You need a sequence of images, okay? That's different. But with an audio, with a short clip of, for example, like 1 second, it contains much more less amount of data, but much more information within it. Okay, so in order to identify using image recognition, you need a sequence of images. You need much more data to understand, okay, this guy is running or this person is running. And what if the person is running behind you? You have to have another 360-degree camera to see that. But audio is a bit different because it's like a spherical kind of radiation. Even if it's behind you, you can understand it. That's why it's in multiple layers, it's different.
But let's imagine that there is a traffic jam, there is rain, and there is a person running.
Yes.
So there is a lot of noise.
So first of all, just before we go with your assumption, in that case, we're not going to do 3D mapping because we're not like we're not going to put our device or in like a danger of being thing, you know. So there's a lot of edge cases. You know, what if earthquake comes and we want there and everything is shaking? How are we going to do? No, there's a lot of edge cases, but in that case, we're not going to
okay.
do the yes.
That was my question.
Okay.
Thank you.
Thank you so much. Thank you.
Okay, thank you,
Thank you.
Alireza.
Thank you.
There is
Thank
another
you.
prize.
Thank you so much. Thank you. Thank you. Thank you.